Good morning, everyone. I'm Tim. I'm one of the application engineers here at Pico Technology. It's nice to see some people in here who we've met previously. Those who we've not met, together with Stuart, who is one of the application engineers on the RF products, we're going to be guiding you through the second round of training. And to start with, we're going to have a recap on the fundamentals. With the SXRTO, the 9400A, it's sometimes a complicated message to get across, and we'd like to think with this training and with the demonstrations that we've achieved that objective. So the objectives we're setting today is that you can describe the functional overview of the PicoScope 9400A. We call this the SXRTO, which stands for Sampler Extended Real-Time Oscilloscope. I'll refer to that as SXRTO going forward. You should be able to describe the key features of the PicoScope 9400A. List at least three customer applications for the instrument. We'll be giving you many more, and Stuart has some great demos lined up as well. So you'll have applications from there as well. By the end of the training session, we'd like to think you'd be able to demonstrate the Pico Sample 4 software. Not necessarily demonstrate the instrument, but the software is available from download from our website. And as you will find out in the training, you can run that in demonstration mode. So what I'd like to do is start with a recap on the previous training. And looking at this slide, you can see there's three different oscilloscopes there. And these are separated by sampling technology. So we have the real-time instrumentation, and I'm showing an example here of the 6000E series. We then have the traditional sampling oscilloscopes, which are the 9300 series. And we have the SXRTO. The SXRTO is where we'll be concentrating on going forward. One of the big things when a customer comes to you is the initial pre-qualification of the instrument, and we're looking at real-time oscilloscopes versus the SXRTO. And unusually, I'm going to start off with the weakness because that's the first level of qualification. If the customer comes in and is looking for data streaming, transient capture, or serial decode, at that point, we would know he needs a real-time instrument. Everything else to the left of here, we should be able to use the SXRTO. And the big advantage of this is we can do that at a much lower cost for the same bandwidth as a real-time oscilloscope. I've emphasized here we're able to view the trigger, pre-trigger, and trigger from channel. That's just differentiating it from the sampling oscilloscope, the 9300 series, where that's not possible, as we'll show in a slide moving forward. Everything else on here we should be able to use the SXRTO for, and at a very competitive price against a real-time oscilloscope. Just have a quick run through the applications. First of all, let's look at signal analysis. We're looking here at electrical standards testing, and an ideal scenario here is pre-compliance, which we'll come to, both in the slides and in the demonstration. And here, generally, customers looking for eye diagram analysis and statistical analysis. A big part of the testing that we come across is RF component testing, where we're looking at filters, amplifiers, cables, connectors, switches. And again, you'll see some examples on how the product fits very well into this area. Research and development, looking more into microwave and RF characterization, high energy physics, digital designs, and of course, traditional radar, but also modern radar going forward. The same areas applying to semiconductor testing. Here, one of the areas is high energy physics, and one of our big applications for this particular oscilloscope, like many of the PicoScopes, is in education, particularly with universities and research with the 9400 series. Pre-compliance testing is a big part of what we do, and here where the customer wants to test products to a standard before they send them off to a lab for actual compliance testing, which generally costs quite a lot of money per hour for that facility. As you will see later on, we have a wide range of masks available in the PicoSample 4 software. The PicoSample 4 software is available for download from our website, and as you will see, we can also run that in demonstration mode on the PC itself. We're now looking into high-speed digital communications and telecommunications. It's a growing part of what we do, particularly with PAM4 testing, which has been coming up recently. There have been 3 or 4 applications where we've been involved in this. So it's a slight deviation from typical oscilloscope testing. It takes us more into the telecoms area, but please do look for applications here. Manufacturing, again, an area we get involved in, both with automatic test systems and limit and mask testing, make sure we're applying to conformance. An application I've had here is where a customer's testing filters, and they'll have 1 or 2 filters they'll test out of maybe 30 or 40, just to make sure that they reach the compliance. And again, you can then use the FFT within the system to tune the filter. So with those applications in mind, I'll just run through some of the key features of the 9400 series. We have instruments going from 5 to 33 gigahertz bandwidth. They all come with 12-bit vertical resolution, so that gives you a high level of resolution for analysing the signals. Presently, we offer 2 or 4 analog channels. The 9400A series are all 4-channel. The 9400 series, we do have a 2-channel instrument. We go up to 5 terasamples per second effective sampling rate and better than 1.5 picosecond jitter. There's a range of automated measurements within the software for sine, pulse, return to 0, non-return to 0, and again I've inserted PAM4 here, which seems to be coming up regularly. We have mask testing with over 204 masks available. I'll be running through a little of this in the slides, and we'll see more of this in the demonstration. Histograms is a large part of what we're asked for, and again I'll be covering that later in the slides. We do have a clock recovery option, which is not really an option that's taken up very often with the instrument. Now we've gone up to the higher bandwidths of 33 gigahertz, this is more likely to feature going forward. Like all PicoScope instruments, it's a Windows PC-based instrument. And we also have a documented API, so you can run scripts. Again, within the software download page, there's a documentation section, and you can download the software development kit and also the programmer's guide. I'd just like to have a quick refresh on the SXRTO sampling now and moving into triggering. So starting on the bottom line here in ETS or extended time sampling mode, the instrument provides most of the measurement capability of a sampling oscilloscope, but without the complexity of the setup. Here you can see the diagram where we're using extended time sampling and taking samples to build up a representation of the incoming waveform. The instrument will also work in real time up to 500 million samples per second. Nobody would really buy the instrument as a real-time instrument for that respect, but it's useful to know that it does have that feature, which could be an additional oscilloscope within a lab that's available in that respect. I'd just like to cover triggering now, because this comes up with the competition. The SXRTO does trigger on the input signal like a real-time oscilloscope. The difference is it uses analog triggering, whereas a real-time oscilloscope uses digital triggering. As you will see in the diagram I'm going to show, it will have a separate analog triggering circuit. This will result in a free-running ADC that can capture and store information, pre-trigger and post-trigger, exactly like a real-time oscilloscope does. But one thing that's often argued against us is that a real-time oscilloscope has higher trigger resolution than the SXRTO due to the sampling methodology. This in fact is not true in reality, because the triggering is limited by the ADC's sampling rate. With the SXRTO, the analog triggering system, we can actually achieve a much higher time resolution going into the range of terasamples per second. And again, when you're demonstrating the instrument, if that's head-to-head against a real-time instrument, you'll find that argument's not valid. So here I'm actually showing a block diagram of the 9400 series architecture. You can see we have 4 channels here, which are each 50 ohm, and we have the trigger pick-off available on each channel. We then go into a track and hold circuit, which is 5 gigahertz, before moving on to the data path for each channel. Just a reminder here, we are looking at repetitive signals and repetitive data patterns. The trigger point is displayed and also is the pre-trigger. You can see on the bottom line here, we also have a trigger out, and you can also take from the track and hold circuits internal triggering as well. In the next slide, I want to compare this to the sampling oscilloscope. Here we can see the 9300 series, which has a different architecture. The signals are going straight into a diode sampling bridge before going on to the track and hold circuits and the data paths. And again here, we need to bear in mind that this is repetitive signals. The complexity comes with the 9300 series, our sampling scopes, that we do need a separate trigger for this to operate. And you cannot display a pre-trigger or no pre-trigger detail either. So there is a complete differentiation here in the architecture. One thing with the 9300 series, we do have TDR available, and there is an optical instrument, which again could be a good questions in the customer pre-qualification stage. When a customer comes in and starts asking questions, one of the things that does come up is eye diagram. So I'd like to just cover the basics of the eye diagram in an overview. The eye diagram provides a comprehensive view of signal integrity. So what we're looking at here is noise, jitter, reflections, ringing, ISI or intersymbol interference, and then power and ground coupling. This is how we acquire an eye diagram. We build up a number of serial acquisitions of the waveform database, starting to the left, resulting to the eye diagram to the right. So it's built up over a number of samples. Then this is displayed in the 9400 software. In this slide, you can see a full scale view of the eye diagram. At the bottom line there, you can see the different menus. When you left or right click on a menu, you can actually add the menu to the left side or the right side of the diagram, as we will demonstrate later. In this, for this instance, I've not actually put up any menus, so you can see the full screen version. The value of an eye diagram comes in mask testing. So with the mask test, it allows us to quickly characterize noise, jitter, aberrations, rise time, and fall time. With the onboard mask capability, you can see on the right-hand side here, I've inserted the mask test setup menu, and you can see we have standard masks, auto mask, or we can do an edit mask where you can create your own mask. And again, these would be used for pre-compliance testing. Here I've selected PCI Express. Then you drop down to the right-hand side, you can see all the different masks available. And the latest mask count we have is 204 for the 9400 series. Here we can see with the 9400 GUI, I've inserted the menu to the left-hand side for the mask test, and you can see the mask test here. We'll see more of this, how this actually runs in the demonstration going forward with PCI Express. To the right-hand side, I've inserted a table that shows all the different masks available for the different serial data systems that we cover. I'd just like to briefly touch on histogram. So histogram is a probability distribution diagram. The right-hand side shows how we can configure this. We have vertical and horizontal, and then you can set limits, and you can look at a linear or a logarithmic scale, and you can also use the API here as well. And this is how the histogram will look in the 9400 series. You can see we've inserted that in the vertical plane from the left-hand side. I've enlarged that at the bottom scale here into the diagram, and you can see we're actually showing 78.2 kilohits per second. Fast Fourier Transform, or FFT, is available. You will actually find it in the Maths menu, and if you go to the bottom tab, and you will then see FFT comes up on the right-hand side of the menu. The reason we would like to use FFT with the 9400 series is to find crosstalk issues and distortion issues. Recently I had a customer who's using it for tuning filter circuits to filter out certain harmonics. They use that in a manufacturing line, and again it's part of the quality control procedure where they can check each filter in turn, and if necessary they can go through each filter if they're not meeting manufacturing requirements and do some tuning on there to filter out the harmonics. No oscilloscope is complete without comprehensive measurements, and we have a range of comprehensive measurements available in the 9400 series, both for the standard measurements as you would expect, trace-to-trace measurements, and also eye diagram measurements. So starting off with the Measurements tab, you can see here we have parameters or statistics. Parameters give an instantaneous view. Statistics record that over a statistical time base. You can set that for repetitive or single shot. You can see the range of measurements here, both in the X-plane and the Y-plane, are quite comprehensive. If you look along the top line there, you can see we have parameter, definition, and limit tests, which I'll just enlarge on. We also have trace-to-trace measurements. You can see here when I've clicked, we've lit up the trace-to-trace bar. Taking that forward, you can then see the trace-to-trace measurements which are available. Typically, you're looking at phase and delay, and they're all available on the 9400 series. Looking at the definition, this is where the customer can define the measurement how they would like that, looking at thresholds, and we can set thresholds and margins. Taking that forward, you can then do limit testing. So we have the limits that are set. You can run an automatic test, and you can see the action at the bottom there. We have a beep, or you can also set up an application to run using the API. Not forgetting eye diagram measurements, I've gone to the measurement screen here, added eye diagram measurements, and here you can see jitter, which we're measuring. The range of measurements is quite comprehensive. Usually customers are asking for jitter and rise time, and we have jitter peak to peak and jitter RMS available. So let's just take a quick look at the instrument and software. The 9400A series is recently launched, the 9404A-33 GHz within earlier this month. This is showing the front picture of the 9404A-25 GHz instrument. You can see we have the 4 channels at the input there, all SMA and 50 ohm. We have the trigger input if we want to bring in an external trigger, or you can trigger on channel. The rear panel shows the USB or LAN connection. Typically we're using USB, but it's also possible to use LAN connection, and you can see recovered data and clock outputs together with the power supply. You'll notice the 9400A series case is different to the 9400 series. With these instruments, you need to download PicoSample 4 from our software download page. Here I'm showing this where we've using the mass test, and if you click on the mass test with the mouse on the left-hand side, the display comes up to the left-hand side. In the next display here, I've gone to eye diagram, and if you click on the right side, you can then see the menu there. So you can have one menu, you can have 2 menus, or you can go to full screen and have no menu at all. I mentioned at the start of the slides that we have a demonstration utility which is available in the software. I certainly carry this about on my PC, and if I'm doing a demonstration, say for a VNA or one of the PicoScopes, it's always useful to have the demo utility. Then you can run through the features with the customer. Please do use this. It's a very useful feature and can often then lead on to an actual demonstration going forward. So that's me done with the slides. I'm going to hand back to Gemma now.
Lovely, thank you, Tim, and hello everyone. We're now going to show you a 5-minute AI-generated video. This video shows how an engineer defines the right oscilloscope for their application, showcasing a typical persona for the PicoScope 9404A-06 RTO. After this video, Stuart Mellis will be doing some live demonstrations for you all. So we hope you like this video. Thank you.
Hey Stuart, I'm wrestling with some high-speed signal integrity issues on our new gigabytes per second data comms project, and I'm really trying to leverage our own tools. I've been eyeing up the 9400A-06 RTO, but I want to make sure I'm fully clued in on all its advantages.
Absolutely. It's always good to see our own engineers using our flagship sampling scopes. The 9400A-06 RTO is exactly what you need for those kinds of problems. What's giving you grief right now?
Well, first off, the signals are incredibly fast. We're talking pulse transitions in the picosecond range and data rates up to 8 gigabytes per second. I need absolute clarity to debug, and I'm pushing our other scopes to their limits.
That's precisely where the 9400A-06 RTO shines and why we designed it that way. It's our sampler extended real-time oscilloscope. The genius here is its ability to seamlessly combine true real-time sampling for transients with random equivalent time sampling for repetitive high-bandwidth signals. For those ultra-fast transitions you're seeing, our 33 GHz models can capture pulse and step transitions down to 10.6 picoseconds. That's a huge competitive edge in terms of resolution.
Right, random equivalent time sampling. So it builds up the waveform over many acquisitions. Does that mean it's only truly optimized for repetitive signals?
Good question, and it's a common one. While random equivalent time sampling is phenomenal for repetitive signals, giving you an effective sampling rate up to 5 terasamples per second, which is 0.2 picoseconds resolution, letting us capture incredibly fine detail, the sampler extended part is crucial for our users. At lower time-based speeds, it behaves like a true real-time oscilloscope, capturing single-shot events with fantastic 12-bit resolution. As you increase the time base, it intelligently switches to random equivalent time sampling. So we've given our customers the best of both worlds in one instrument.
Okay, that makes sense. And vertical resolution? My current development kit scope is only 8-bit, and seeing subtle signal variations, especially with noise, is a challenge.
Another major benefit we focused on during its development. The 9400A-06 RTO features 12-bit ADCs across all models. That's significantly more vertical resolution, allowing you to see much finer detail in your waveforms and more accurately characterize your signals. It helps our customers and us in identifying subtle anomalies that an 8-bit scope would completely miss. We put a lot of effort into making that high resolution usable.
And triggering. With such fast data, getting a stable trigger is often a nightmare, even for us.
We made sure the 9400A series has a super robust triggering system. It offers a built-in full bandwidth trigger on every channel, with pre-trigger random sampling capabilities. This means you can see what happened before the trigger event, which is incredibly useful for root cause analysis of intermittent issues. Plus, for your datacomms work, we offer optional clock recovery triggers up to 11.3 gigabits per second, and even recovered clock and data outputs. That's a feature our customers in telecoms and high-speed digital really appreciate.
Clock recovery would be a lifesaver. Our current method for debugging is a bit of a workaround. What about specific applications? We do a lot of eye diagrams and mask testing in this department.
The 9400A-06 RTO was specifically designed with that in mind. It excels at eye diagram mask and limits testing up to 16 gigabits per second. We built in comprehensive measurements, zooms, data masks, and histograms, making it super easy to perform those kinds of pre-compliance checks. Think Ethernet, HDMI, PCI, SATA, and USB 2. It's purpose-built for those high-speed digital standards, which our customers are constantly pushing.
That sounds exactly like what we need for validating our prototypes. And since it's one of ours, I know it's PC-based.
It's a core part of the Pico philosophy, USB connected, leveraging the power and display of your PC. This translates to a more intuitive and configurable user interface, the ability to use multiple monitors for analysis, and easy integration with other software for advanced analysis and reporting. It's also remarkably compact and portable for the performance it delivers, which our field application engineers love.
So, if I'm understanding this right, the main selling points and the internal benefits are incredibly high effective sampling rates and bandwidth for super fast signals, excellent 12-bit vertical resolution, versatile triggering including pre-trigger and clock recovery, and a strong suit for eye diagrams and digital pre-compliance testing, all in our familiar PC-based package.
That's right, Adriana. It's a testament to the engineering effort we put into it. It's a powerful tool that offers a significant advantage in high-speed digital design and characterization, semiconductor testing, and general high-bandwidth signal analysis, enabling us and our customers to get much more accurate and insightful measurements on those tricky signals.
Thanks, Stuart. This was really helpful. Good to know we've got such a capable instrument right here in our own lab. I'll get it hooked up to my bench today.
And a very good morning to you. My name is Stuart, and I have the absolute pleasure of guiding you through the demonstrations on PicoSample 4 today. We will be looking, interestingly enough, at our new and our latest model, the 33 gigs, and we'll be demonstrating with that. So with no further ado, I will first explain my setup. So as you can see, I've got on top of the SXRTO, I've got a pattern generator that is capable of generating a pattern up to 14.6 gigabits per second. This gives up a differential output, and we're going to be using this to generate a PCI Gen 3 Express data pattern. You'll also notice that I've also got this black module here is a very high speed pulse edge generator. And we're going to be using that to actually show the actual fast response time of the 33. Now, one of the unique features of the 9404A-16 is its triggering capability. So I just want to expand on that a little bit. So on any of these channels, I can trigger directly up to 2.5 gigs. So channel 1, 2, 3, and 4. If I needed a higher frequency trigger, we can still trigger off the channel, because what we can do is use the divide by 4 capability that's within the software. So theoretically, you can trigger on any channel, namely channel 1, 2, 3, or 4, up to 6 gigahertz. If your signal is higher in frequency than that, you can switch through to our pre-scale trigger, which you'll see on the right hand side here, and that will allow you to go on the 33 gig model, and the 25 gig model will allow you to trigger up to 20 gigahertz. So its triggering scheme is very, very robust in terms of its capability. So now what we're going to do is start looking at the software in a bit more detail. You'll notice on the screen now we have a fast edge. Okay, so I just want to give you a little explanation on why it's so crucial for the fast edge to be characterized. So it's useful in testing lab instruments and probe frequency, bandwidth, and rise time. So the one we're using, it has, in theory, and we're going to prove it is 30 picoseconds by using the capabilities of PicoSample 4 and the Leo Bodner pulse generator. Measuring a fast edge with an oscilloscope is crucial for characterizing digital signals and pulses and the performance of high-speed electronic circuits. What is a fast edge? A fast edge refers to a rapid transition in a signal's voltage level, the rise time. Okay, so what we're going to do is make a measurement in due course. And why I measure these fast edges? Basically look at digital signal integrity. In other words, digital systems, fast edges are really essential, actually, for reliable data transmission. Poor rise times or force times can lead to really bad signal degradation, as Tim mentioned earlier, and also bad inter-symbol interference numbers and timing areas. We also want to look at circuit performance. The rise and fall time of a circuit's output can indicate its speed capabilities and limitations. And then, of course, we want to look at component characterizations. Engineers are can use fast edge measurements to characterize the switching performance of transistors, logic gates, and other high-speed components, and of course for troubleshooting. So now let's start going into the software. And what we're going to do is actually look at the first. You'll notice on my screen here, I've got, just to show you there, I've got the Leo Bodner, which is the channel 4, which is currently active. And you can see that I'm going in the rise time. I'm going to change the time base now, okay, to probably 50 nanoseconds. Okay, now you'll see I'm going to go into the measurement functions. Okay, interestingly enough, in PicoSample 4, if I left click my mouse, the measurement dialog will appear on the left. Now if I was to right click my mouse, it would appear on the right hand side, so you can actually define where your measurements appear. So now I'm going to go to statistics, and you'll see I had prepared already our rise time measurement. The rise time measurement, you can see, is way within the specification of the pulse generator, and I am getting a rise time measurement, a minimum of 22.36 and a maximum of 26.59. So you can see that the scope can formidably capture a very fast edge. Okay, so now what I want to do is actually show you the actual jitter spec of the instrument in itself. So I'm just going to close this menu down. So we'll turn off this spec here, and then we're now going to switch to histogram. Okay, if I now turn on my histogram functionality, you'll see there, as I prepared earlier, you'll see the histogram measurement there. So the scope itself is spec for 1.2 25 to 1.3 picoseconds. We are getting a standard deviation of a 1.36 picoseconds. So the instrument itself, its low intrinsic jitter spec is actually, it's very formidable. So that's just to show you a quick example of how we can look and define a very fast edge. So now my next demonstration is we're going to be walking you through a very fast speed measurement. We're going to fully characterize a differential pair of PCI Express Gen 3. So you'll see now channel 1 and 2 are my active differential pairs, and I'm just going to show you the my setup here. I'm just going to pull this over one moment, and you can see that I'm using a pattern synthesizer. Okay, so what we're going to do now is we're going to start building up our story and how we go around characterizing this high-speed data. So first I'm going to do is change my time base, and you can see there, I'm now going to, just one moment, I'm going to switch triggering schemes. In this example, I'm going to use the external phase lock loop output clock, and we can also trigger off the channel. And what you'll find now, if I go to external, and there you go, we have a very nice clean signal. Now, what we can do is we can define its data rate, its pattern length. In this example, I'm going to be using PCI Gen 3, which will appear in due course. And there you can see we've got our pattern of PCI Gen 3. So I'm just going to set I'm doing this live, so I'm going to be setting this up as we go. I probably will be using 50 millivolts per division to look at both my differential pair. Now, the first thing I might want to do is have a look at my D skew in the channels, and you can see that they're not fully aligned, and that the software PicoSample 4 will allow me to have a look at my D skew. So if I go into the measure menu here, I can look at my trace measurements, and what I can do is actually look at how much delay is between channel, and you can see there is some sort of delay. Using mathematical approach and to create the differential signal, that will iron that out. But you could use a D-skew function, or make sure that your cables are identical length. But one of the features in PicoSample 4 gives you the ability to look at the delay in channel 1 and channel 2 with respect to each other, and that's the rise time or the falls time. We can also make phase measurement and gain measurements. So just be aware of that. Just turn that off. I'm now going to go into the max functionality, and what we're going to do now is create a differential signal with the differential output of this PCIe Gen 3. So now if I go to scaling, you can see now turn on, I've got my signal. Go back to function, apologies. And if I subtract, You can see now, and bring that to my scaling. On, just take that up a little bit, and there you can see now, if I turn off channel 1 and channel 2, I'm now left with my differential. So now we can go up and set up an eye diagram for this particular measurements. The PicoSample 4 software has a wealth of measurements built in for characterizing pre-compliance eye diagrams. So what we'll do here is we'll go into the mask test, okay, and I'll show you as a standard. We've got a range of standards. In this example, I'm going to be using PCI Express, but we have Ethernet, we have fiber channel, we have rapid IO, we have USB, we have Zowie. I'm going to be using Ethernet, okay, and then I'm going to, oh, sorry, PCI Express, sorry, I meant to say that, schoolboy error. And then what I'll do now is I'll go down to Express module, and then I'll build the eye. So now if I expand there and then pull this across, what we can do now, if you'll notice, there's an alignment option there, okay, and then if I do an auto scale, I'm hoping in a moment we will be aligned around the mask. Okay. Yeah, to turn that off. Okay. And I want to go to external trigger. Okay. And just move. There we go. Just a bit more. And if we just go 80. And you can see we're slightly failing on the mask, but that's good, because what we want to do with an eye diagram is we actually want to make sure that we are within the polygons. An example, we're not, but you know, this is the point of doing a pre-compliance test, is to make sure that we are, you know, we are working fundamentally within it. So trigger. So what we might want to do is have a look at the pattern length, okay, and look at the functions around pattern length trigger here. So I'm now going to show you some of the capabilities of our bear with me, there we go, nice, mask off. Where's mask? Okay, now if we go into trigger function here, if we go to pattern sync, okay, what this will do will allow me to actually look, the software will look for the pattern length of this pattern here. Okay, and now if I just change time base, and there we can see we have now got the length. This is our PCI Express data pattern, and you can see its data rate is actually 2.92 gigabits. Okay, so one of the features of now that the differentiator here between a traditional sampling scope is what you would have to do is you'd have to, if the clock wasn't around, you'd have to have clock recovery. We have done this triggering off the channel, you know, which is a quite unique feature in that respect. So yeah, I could also do the same on channel 2. Okay, what I'm going to do now is actually show you and do a comparison of the two data sets. So here, if I go to dual YT, and what you will notice is that the data is mirrored. So channel 1 is high and channel 2 is low. So pattern sync is, you know, very, very useful in a number of environments, especially when you're wanting to, you know, wanting to look at your data in a sequence. So when pattern lock is switched to auto detect, the oscilloscope will automatically detect data rate, pattern length, and trigger divide ratio, and then generates the pattern trigger, as we can see there. The oscilloscope can manually detect data rate, pattern length, and trigger divide ratio and generate the pattern trigger. You can also enter the length. So if I go to pattern length now, just go back to trigger, pattern sync there, you can see I can define the pattern length list. Now if I drop that down, I can actually set the pattern length list for that particular measurement. This applies to any of the data standards. We could go through them all today, but what I'm trying to say to you is within the PicoSample 4 functionality, there is a wealth of measurements at your fingertip. Okay, so now I'm going to do is now come out of pattern sync. Okay, and now we're going to look at histograms. Okay, I'm just going to now go back into display and go back to an auto scale there. Right. Just change my time base and move this along a little bit. Okay, so we'll just start with one channel there. And what we will now do is just talk a little around the importance of a histogram and, you know, this functionality. So as Tim was saying in his slides, that a histogram is a graphical representation of the distribution of a set of data in the context of an oscilloscope. So, for example, the vertical amplitude histogram will show the probability distribution of the signal's amplitude values. The x-axis represents the voltage levels, and the y-axis represents the number of times or probability the signal spends at a particular voltage level. Horizontal histogram shows the probability distribution of time-related measurements, such as period, pulse width, or rise or fall times. And of course, the x-axis represents the time values, and the y-axis represents the frequency of occurrence of that. So let's just look at this practically now. So if I now go to my histogram menu, and we start with the horizontal measurement, if I now pull this along, okay, and we want to look at that eye crossing there, straight away you can see I've got my standard deviation, I've got my peak-to-peak hits, and I've got my number of waveforms. So we can quickly and effectively look at our horizontal histograms. Now, this is very useful when we're characterizing our deterministic jitter. So when we're looking at peak-to-peak jitter and RMS jitter. And conversely, when we want to look at vertical, so we might want to have a look at our RMS noise, for example. Okay, the RMS noise actually sitting on our eye diagram there, and you can see we're quickly and effectively looking at these measurements. If there are any other further questions that are needed on PicoSample 4, feel free to reach out to us. I hope you found that valuable. Please do, I encourage you to download PicoSample 4 from our website. And, you know, from my side, thank you very much for listening, and have a nice day.
Lovely. Thank you, Stuart. And thank you to Tim for a great webinar. We hope that you all enjoyed that and have learned a bit more about our PicoScope 9400A series. There haven't been any questions in the chat pod. So if you do have any questions following the webinar, please, like Stuart said, do get in touch. We'll be more than happy to answer those questions for you, either via your distribution manager or direct to the guys here at Pico. So yes, thank you everybody for attending, and we hope to see you for our next webinar soon.